the position of a particular spot varies with time and also where you are on the coil. Because I have this thing that's constantly being produced over and over again and being propagated outwards. So I need to somehow come out with an equation which involves period and wavelength. And you're alive. Such a thing exists. So it all depends on whether you want to start with sine, do a sine or cosine. Just to stick with my notes, I'm going to do sine. I'm going to have some amplitude here times the sine of, well, I have my position piece of it, and then I have my time piece of it. Omega here is the angular frequency. And K here is the wave number. So my period would be, more generically, if you think about omega, if you think about I've got the circle here and I have this arrow, think phasor if you want, I have something that's rotating around. Omega is the angular speed at which it rotates around, and also the angular frequency of the equation. If omega goes up, my period goes down because it's moving faster. So what is the relationship between the period and omega? Or if you need something more concrete, sine of t has a period of 2 pi, because if I do sine versus time, it completes the wave at 2 pi. If I did sine of 2t, when is the wave completed?
4 pi.
4 pi.
All right, we had 2 against 2 now.
It'll be 4 pi because 2 equals, the t equals 2 pi.
So when time equals 1/2, that would be one wave.
You want to know when is 2t equal to 2 pi?
Oh,
As omega goes up, I'm spinning faster, so it takes less time.
so just take pi.
It'd be pi.
Okay.
Or in general, we're trying to figure out when omega t is equal to 2 pi. Well, that happens at 2 pi divided by omega. We get the wavelength based upon the coefficient of our position vector, or our position. I guess it is a vector. Anyone want to throw out the formula for lambda? All right, let me just change the symbol here from T to X.
Two pi over K.
So we have a generic formula right here for a propagating wave. So tapping into this, I know that the speed of the wave is going to be the wavelength times the frequency, or actually probably better, wavelength over the period. My wavelength is 2 pi over k, divided by my period, which is 2 pi over omega, which then just becomes omega divided by k. So if I gave you the equation here, you could figure out the speed of it just by the idea of what omega and k are. Obviously, there's no physics involved here, this is just math. So we need to bring some physics in. Because I don't want you going home being upset that we didn't do enough physics today. Any questions before I erase? We're gonna put over here, V is equal to omega over K, because that will come back. So we talked generically before about how we have this electric field that is oscillating back and forth, creating a magnetic field which is oscillating back and forth. So if I drew my electric field that's oscillating back and forth, as this propagates outwards, this is my electric field with a peak value of, we'll call it epsilon sub, or not epsilon, E for electric field, E sub 0. I guess I used E sub M there, so why don't I stick with my notes? Not that it's gonna be, I don't have both of them involved, but for maximum value. So my electric field, I can write as my maximum value times the sine of kx minus omega t. On top of that, I have a magnetic field that's also being created. Or enough of a contrast in color here, don't want to use that. So as my electric field is moving up and down like that, my magnetic field is moving in and out, it's perpendicular to it. So I attempt to do a three-dimensional drawing here, but however you represent it, just recognize that the magnetic field is in a plane perpendicular to this. That is my attempt at drawing a three-dimensional drawing. Where my magnetic field, this is my magnetic field, with a maximum value of V sub M. So my magnetic field can be expressed as some maximum value sine kx minus omega t. On top of all this, we have two laws that we need to take into account. We have Faraday's law, that the integral around some loop of E dot dl is equal to the negative change in the magnetic flux with respect to time. And then we have Ampere's law with Maxwell's correction, B dot dl is equal to mu naught I plus mu naught epsilon sub naught phi E dt. And for those fans of Gauss's law, sorry, we will not be using those right now. Now there is no normal current here, there are no charges involved, and no charges moving, and so this goes away. This is the more traditional current. What we care about is the change in the electric field or the electric flux. Now I've drawn this like it's, the whole thing exists in two planes here. I mean, it's existing in more than two planes, but this is just sort of a representation. But what I'm going to do is I'm going to take a box here because I need to do a line integral. So I need to take a box and do a line integral. So we draw that box I just drew. And so on the left side of this box that I've drawn over here, the electric field is some value. I'm just going to call it E. And just for contrast. And then on the other side of the box, this thing is really, the width here physically is some infinitesimally small position and difference in x. And so my electric field after it's moved some distance x here, is just gonna be whatever that is plus some infinitesimally small change in the electric field, or electric field strength. Because this box here, it's a virtual box, but it does have dimensions here. I've got a width of some infinitesimally small amount and a height of h. H is gonna go away, so it's not crucial what the value is. And in this particular part, where I've got my electric field going up in the positive direction, my magnetic field is coming out at us. Yes?
You have on the right side E plus what?
dE. Differential in the electric field strength. So my magnetic field is coming out at us. I only care about the part of the magnetic field inside my box there, inside my Amperian loop. So now we can do this. I'm going to be using this equation right here. That first part, it's a line integral, the electric field around the box. I'm basically going to have a starting point and I'm going to go around it. So I'm going to start here. And I want to go in a right-hand direction. I do need to make sure I get that one right. Yeah. So my magnetic field's coming out. I'm going to be doing my loop in a counterclockwise direction so that the thumb points outwards. So I start here. I'm just going to call this path A, B, C, and D. So my line integral here is just E dot dl along path A plus E dot dl along path B. I guess I can integrate plus E dot dl along path C plus integral E dot dl along path D. And that puts us back to where we started. So doing a line integral around the full loop, I'm just doing each segment separately. And that's going to be equal to the negative change in the magnetic flux with respect to time. Actually, we can narrow that down a little bit better. That magnetic flux is B dot A. Questions to hear? All right, so along this path right here, this first path along A, what is the direction of my electric field?
Go right.
Why?
As you come out, it curls around. So at the bottom it would be.
Realize it's the electric field making that magnetic field. It's not magnetic.
Oh, it's
field.
perpendicular too.
Yeah. So think about the section that I drew my box in. What's the direction of the electric field?
Up.
Yep. The electric field is up this entire time.
Okay.
But my length here, my DL, is that way. So DL and E are perpendicular to each other in this first section, so that's 0. E is perpendicular to, well, basically the length of A. Along B there, what's the direction of my electric field?
Same direction.
Yep, up. And my path is also up, so this is just going to be E plus DE, that's the strength of my electric field, times the length there, H. What about along path C? I'm not going to the left as I'm working my way around. What's the direction of the, so I did B there, now I'm doing C. What's the direction of my electric field along this path?
Still up.
Yep. And my path is that way. They are perpendicular once more. 0. And then on this last bit, I'm moving down back to my starting point. The electric field and my path are in opposite directions, negative EH. Now, in this section right here, I got a negative. B dot A, my area vector and my magnetic field are in the same direction. So I can get rid of the dot product aspect. It's just, B times A. A is not changing with time, and so this just becomes dB dt. Area is the area of my box. Well, it's h times dx. So this becomes negative h dx times dB dt. Give you a chance to catch up and ask questions if you have. All right.
So are we finding the speed of light from substitution, more or less?
Well, technically we're finding the speed of an electromagnetic wave.
Okay.
And it turns out that's the speed of light. Is that sufficient?
Yes.
Okay.
When we found the speed of an electromagnetic wave, did we already have a calculation for the speed of light?
It had been found experimentally already at that point.
Okay.
And so that's why Maxwell speculated that light was an electromagnetic wave.
Someone spent their entire life on what you're about to do in about 2 hours.
I feel that way about Kepler. I mean, he spent 40 years of his life coming up with his laws, and we can now do it with, if you know calculus, based on Newton's laws, you can do it in an afternoon.
Mhm.
But I guess that's always the first person to come through to do it. Takes a little bit longer.
Right.
And it took Newton a little bit longer because he had to invent calculus in order to do it. Yeah, I said Newton did it. You Leibniz fans out there, just keep quiet. All right, so on the left-hand side over here, I distribute the H, and I have an EH, which will cancel out with that one. So what I'm left with is HDE. And I'm gonna put a little bit of space there because DE goes together, it's the differential, is equal to negative H dx times ddt of my magnetic field, which is Bm sine kx minus omega t. H's cancel out, which is fortunate, since it's an arbitrary distance there. I have my dx here, so I'm just gonna divide by dx to get myself a derivative on my left-hand side. So I have dE dx, bring that over. Which is d times, or ddx of the magnitude of my electric field times the sine of kx minus omega t. And that's going to be equal to what I have left over here, which is ddt of my magnetic field. And now we just do some calculus. All right. What is that? E. So then, I assume you said E.
Yeah.
Okay. So far, so good.
This is per dx, so
E
K.
cosine KX
that negative there, so negative.
So positive omega and the negatives cancel out.
Yeah, I'm gonna go ahead and put that in there, the two double negatives. So I got that negative here, and then I've got a negative omega there. Okay,
Cosine kx minus omega t.
well, we get rid of some nasty stuff there that we don't have to worry about. Fortunately, the trig function goes away. My minus signs go away. And I'm left with this magnitude of my electric field times K is equal to magnitude of my magnetic field times omega. I know that the speed, as we talked about earlier, is omega divided by K, so let's go ahead and set that up. So omega divided by K is equal to the magnitude of my electric field over the magnitude of my magnetic field. And we're at the halfway point.
For us.
Questions up to here, because I need space, I'm gonna erase this. We're gonna do something very similar, except we're gonna use Faraday's law. I'm sorry, that was Faraday's law. We're gonna use the Maxwell correction to Ampere's law, the Ampere-Maxwell equation, in order to get the other part of this. We'll combine the two, and we'll end up with a nice little formula.
Confused as to where the, right after the dx, that portion came from. 'Cause-
It's the derivative of the electric field, and I established that.
Okay, I see. Gotcha.
Yeah, we are working with the assumption that we have this oscillating field.
And that is times the derivative.
This is time derivative on this side and the position derivative on that side.
I'm just looking at this step above it, it looks like they're combined, is that right?
I have the dx here, but it's not really associated with anything, so when I divide by dx, I get de